Welcome to another episode of Terry's Notes. And today we are going to be looking at chemical energetics. Now, in any chemical reaction, we have reactants on the left-hand side and we have products on the right-hand side. For example, if we have A plus B reactant to produce C, A and B on the left-hand side of the equation represents the reactants and C represents the product in this case. Now, in the reactants, we have bonds being broken and energy is required in this process. And when the product is formed, when the product is formed, this is a bond making process and energy is released in the bond making process. So you need to know that in the bond breaking process, energy is required. And in the bond making process, energy is released. Now, bond making and bond forming process, they occur at the same time in a chemical reaction. Now, we have two kinds of chemical reactions. We have endothermic reactions and we have exothermic reactions. The overall reaction is endothermic if the energy absorbed in breaking the bonds is greater than the energy released when bonds are formed. So you need to be able to give a definition for an endothermic reaction. Now, in an endothermic reaction, energy is absorbed from the surroundings. So for example, when potassium nitrate salt is added to water in a beaker, the outside of the beaker feels cold, indicating that energy is being absorbed from the surroundings. So this is one key feature of an endothermic reaction. The temperature of the reaction mixture drops as energy is absorbed from the surroundings. And another key feature here is that the amount of energy required to break bonds is greater than the amount of energy released when the products are formed. Now, in the case of an exothermic reaction, the overall reaction is exothermic if the energy absorbed in breaking the bonds is less than the energy released in forming the bonds. In an exothermic reaction, energy is released to the surroundings. So when sodium hydroxide pellets are added to water in a beaker, the outside of the beaker feels warm, indicating that energy is released to the surroundings. So far we've said that endothermic reactions absorb energy from the surroundings and exothermic reactions release energy to the surroundings. Now, you need to understand the concept of heat or energy content of a reactant or product, and this is what we call enthalpy. So you're going to meet this term several times, and the symbol we use to represent enthalpy is a capital H. Now, it is difficult to measure enthalpy directly, so what we do is we measure enthalpy changes. Okay, and we represent enthalpy changes by the symbol delta H. So the enthalpy change is really equal to the energy content of the products minus the energy content of the reactants. Mathematically, we write it as this: delta H is equal to energy content of the products minus the energy content of the reactants. So, for an endothermic reaction, the enthalpy of the products or the energy content of the products is greater than the energy content of the reactants, in which case delta H is positive for an endothermic reaction. In the case of an exothermic reaction, the enthalpy of the products or the energy content of the products is less than the energy content of the reactants. Therefore, delta H is negative for an exothermic reaction. Now, you will be expected to draw energy profile diagrams, and basically on the y-axis we have energy, right, and this is usually written as kilojoule per mole, and on the x-axis we have reaction pathway. Right now, this curve represents an energy profile diagram. On the left hand part of the curve we put the reactants, and on the right hand side we have the products. Now, the difference in energy level between your reactant and your product is called delta H. So this is delta H, and it's simply the distance between your reactant and your product. So this is delta H, and the difference between the energy content of the reactants and the highest point on your energy profile diagram represents your activation energy. So this represents your activation energy. So let us go back to an endothermic reaction. Now, in an endothermic reaction, we said the energy content of the products are usually greater than the energy content of the reactants. So therefore we see products will be at a higher level than the reactants. Okay, so you have products here and you have reactants here. Now, the activation energy is the difference between your reactants and your highest point on your graph. So this line here represents your activation energy for this endothermic reaction, and the difference between your product and your reactant, that is this distance here, is what we call the enthalpy change, right? Now, enthalpy change, we said before, delta H is equal to the energy content of the products minus the energy content of the reactants. In this case, it is H2 minus H1. And if you look at where they are in relation to each other, if we take H2 minus H1, we'll get a positive value, right? And that's why we say that the enthalpy change is positive for an endothermic reaction. In the case of an exothermic reaction, things are slightly different. So we have energy content of the reactants being H1, we have energy content of the products being H2, and we see that H1 is greater than H2. Therefore, if we work out the enthalpy change, it'll be H2 minus H1, and because H2 is smaller, the enthalpy change is going to be negative, right? So for an exothermic reaction, the enthalpy change is negative. And again, the difference between the reactants and the highest point is called the activation energy. And the difference between the enthalpy of the reactants and products, as this distance here, is called the enthalpy change. Now, we also need to know the effect of a catalyst. How does it affect the energy profile diagram? Now, the first thing we need to know is, what is a catalyst? A catalyst is something that is used to speed up a chemical reaction, and what it does, it provides an alternative pathway for the reaction. But this alternative pathway has a lower activation energy. So you can think of the activation energy as the energy barrier required, or the energy barrier that prevents the reaction from taking place. Once you supply this energy, the reaction is going to take place, right? So activation energy, or the energy barrier, is the minimum energy required to start a reaction. and we need to know the effect of a catalyst on the energy profile diagram. So if we look at this energy profile diagram, we have this curve here represent the energy profile diagram of an exothermic reaction, because the enthalpy of the products is less than the enthalpy of the reactants. And this one represents, this is without the catalyst. So this is without catalyst. And when we add a catalyst to the reaction, what is going to happen is that we notice that this curve here represent the energy profile diagram for a reaction that is using a catalyst. So this is with the catalyst, and if you notice, without the catalyst, the activation energy was represented by this line, and with the catalyst, the activation energy is now this line. Okay, and notice that both curves start at the same point, because remember we said this is the enthalpy of the reactants, and both of them end up at the same point. All right. So in this video, we looked at the difference between an endothermic reaction and an exothermic reaction. We also looked at energy profile diagrams. You need to know that in any chemical reaction, we have bonds being broken and bonds being formed. When bonds are broken, energy is required. And when bonds are formed, energy is released. So if more bonds are formed than bonds are being broken, then the reaction is going to be an exothermic reaction. And if more bonds are broken than bonds are formed, then the reaction is going to be an endothermic reaction. You also need to remember that in an endothermic reaction, the enthalpy change is positive, and in the case of an exothermic reaction, the enthalpy change is negative.